In this detailed example, we're going to look at sampling and sampling distributions. And we're going to do something a little bit different than we've been doing. I've actually created a computer program that's going to approximate the sampling distribution based on a randomly generated variable. And so what I've done is I've created a variable that follows a uniform distribution, a continuous uniform distribution. Here's what it looks like. It's based on 800 cases, and I just randomly generated this variable. I'm going to call the variable u. The variable has a population mean of 0.5 and a standard deviation in the population of 0.29. And so what I'm going to do is I'm going to create a sampling distribution, an approximation of a sampling distribution of this variable. And I'm going to do it in the following way. I'm going to take repeated samples of the same size from these 800 cases, and each time I'm going to calculate the sample mean. Now it ought to be something close to 0.5, but there's going to be some variation. And I'm going to stack each of those different sample means into a single data set, and I'm going to graph the resulting distribution. And that's going to be an approximation of the sampling distribution. So let's try that. So in the first iteration, I'm going to take this variable, and I'm going to create 200 samples, each one of them independent, and each one of them a size 100. And I'm going to graph the resulting distribution. So if I run this, notice that for each of the 200 samples, it's going to calculate the sample mean. And we're going to graph the resulting distribution of sample means. And so notice a few things. So here we have a histogram of the distribution of sample means based on 200 independent samples of size 100. Remember that the true population mean was 0.504. Here we see that value is the center of this distribution. Notice that the distribution is bell-shaped, meaning that some sample means are below the value 0.504. Some values are bigger than that value, 0.504, but most are in the middle. And so what we can see is that we have a normal distribution of sample statistics, in this case sample means, centered around the value of the true population mean. Although some are smaller than the population mean, they're not very likely. And again, while some are bigger, they're also not very likely. It's most likely that the sample mean is going to be equal to the true population mean, because most of those means are in the middle. Now, notice also that I've taken the mean of the sampling distribution. That is, I've taken the mean of all 200 sample means. And I got a value of about 0.50. Notice that's equivalent to the true population mean, or very close to it, which again was equal to 0.504. I've also found the standard deviation of the sampling distribution. That is, I've taken all 200 sample means and I figured out how much variation there is across the sample means from sample to sample. And so I got a standard deviation of sample means of 0.003. And I calculated something called the standard error, which is basically equal to the true population standard deviation, which you'll recall was 0.29. divided by the square root of the sample size. And so we have a sample size of 100. The square root of 100 is 10. And so 0.29 divided by 10 gives me roughly 0.03 if I round it. Right? So we have basically the amount of variation in the sampling distribution equal to the population standard deviation divided by the square root of n, which is called the standard error. And so what could we say about this? Well, basically what we have here is a distribution of sample means. It tells us something about how much variation we have across samples. Now, where does the variation across the samples come from? Well, by pure chance, right? The only difference between one sample and another sample is that by random chance, somebody with a high value on this variable happened to get in or out of the sample. And so by random chance, each sample that you draw is going to be different from the value of the population. And so this is telling us basically how much sampling error we can expect to have from sample to sample. Now, of course, when we actually do research, we only take a single sample. But using this idea of a sampling distribution, we can figure out how much our particular sample might deviate from the value of the true population parameter if we know something about how much variation we have across samples, or how much our standard deviation is equal to, based on the distribution of all possible samples of the same size drawn from the same population. Advancing this detailed example forward just a little bit, let's see what else we can learn about sampling distributions from this exercise. So let's look what happens when we keep the size of each individual sample fixed, but we vary the number of samples that we take. So let's run this again using 5 samples of size 100. And so here we go. Here are our 5 samples, each with a different sample mean. If we look at the resulting distribution, well, it doesn't look like there's any kind of real pattern here. But what happens if we use more samples? And so again, instead of using 5 samples of size 100, let's use 15 samples of size 100. So again, it doesn't really look like there's much of a pattern here, although something is sort of starting to form. Let's kind of push this forward a little bit. Instead of using 15 samples, let's now use 25 samples. Okay, so here are 25 samples, each with a different sample mean. We're going to graph the resulting distribution. Notice that it's starting to look more like a normal distribution. And so this is illustrating something called the central limit theorem. The central limit theorem tells us that as long as we have a sufficiently large sample size, about 50 or more, in this case we have 100, so that's plenty sufficient, the resulting distribution of sample statistics is going to be a normal distribution. And so what I've been doing in this detailed example is I'm approximating the sampling distribution. The true sampling distribution is based on all samples of the same size. So that could be a very large number. It's not just 25. It could be thousands of values. Let's see what one looks like if I use 200 samples of size 100. So for each of those 200 samples, I'm calculating the sample mean and I'm graphing the resulting distribution. So notice that as I increase the number of samples, I'm getting a more and more pronounced bell shape. And so this is illustrating the idea of the central limit theorem. Okay, advancing this detailed example forward yet again, now let's think about what happens as we increase the size of each sample, but we hold the number of samples fixed. So let's take 200 samples, each of size 5, and we'll run that. Okay, so for each of the 200 samples, each based on independent samples of size 5, here's the resulting distribution. So again, it's bell-shaped, it's centered around the mean. The population mean is roughly equal to the mean of the 200 sample means. But notice here that the standard deviation, which is again kind of very close to the standard error, is equal to 0.12. Remember that number for a second. Let's see what happens as we increase the size of each of these samples. So let's take, instead of 200 samples of size 5, let's take 200 samples of size 10. Okay, so for each of the 200 samples, each of size 10, we're calculating the sample mean, and then we're going to stack them into one data set and graph the resulting distribution. Okay, so now you can see that we've got pretty similar results. We still have a bell-shaped. It's still centered around the value of the true population mean. The mean of the sampling distribution is still roughly equal to the mean of the population mean. But notice that now the standard deviation of the sampling distribution and the standard error are a little bit smaller. So now, rather than being equal to 0.12, the value is 0.09. And so what seems to be happening is that as we increase the size of each sample, the variation across the samples is getting smaller. Let's run one more test. Let's run 200 samples, each of size 50. So we're going to take the sample mean for each of those 200 independent cases, each based on samples of size 50, and we're going to graph the resulting distribution. And so again, notice that we have approximately a bell shape centered around the value of the true population parameter. Population mean roughly equal to the sample mean. The two should be identical if we took all possible samples of the same size. But notice here that the standard deviation again is getting smaller. So what's going on here? Well, we can generalize by saying that as we increase the size of each sample, the amount of variation in the sampling distribution is going to go down. That is, more of the sample means are going to be clustered around the value of the true population parameter. And that makes sense because for each sample, if we have a bigger sample size, we should be able to better estimate the value of the true population mean, right? So it makes sense that we have less variation as we increase the sample size. In other words, we have a sampling distribution that's more tightly clustered around the value of the true population mean. And that's why we have to calculate the standard error by dividing the true population standard deviation, which accounts for the amount of variation in the variable in the population, by the size of the sample, and of course we take the square root of that value, because the size of the sample determines how much variation we have in the sampling distribution. So we have to account for that by dividing the population standard deviation by the square root of this value. As a final set of observations, let's see what happens when we use random variables in our population that follow some other distribution. And so for the first set of examples, I used a uniformly distributed variable. What if I had some variable that followed a different distribution? And so, for example, I also created a random variable that follows something called a binomial distribution. It looks something like this. And so it takes on values between 0 and 5. Again, there's 800 cases, has a mean of 2.53 in the population, with a population standard deviation of 1.12. Let's see what happens when we calculate a sampling distribution for this based on 200 samples of size 100. And so it calculates the mean for all 200 cases and it graphs the resulting distribution. Again, what we find is the same kind of thing. We have a normally distributed variable centered around the value of the true population mean, in this case 2.53. The population mean is roughly equivalent to the mean of the sample means, in this case based on 100 size samples, 200 of those. And we see that the standard error equals the standard deviation of the sampling distribution. And so what if we did this for a different variable that had an even different shape? Another variable that I created was something that follows a Poisson distribution. And so here's my Poisson variable. Notice that most cases are at 0, some are 1, some are 2, but increasingly fewer are at larger values. Again, this is based on 800 cases. The mean here is 0.4, and the population standard deviation is 0.61. What happens if we take and create a approximate sampling distribution for this variable? Well, here I have to actually use more cases, so I've created a sampling distribution based on 500 cases, each of size 100. So this will take a little bit longer to run. But you can see it's going to calculate a sample mean for each of the 500 different samples. It's going to stack them all into one data set, and it's going to graph the resulting distribution. And we can see, again, it's more or less a normal distribution. Again, if we had all possible samples of size 100 instead of just 500, this should look like a really pronounced normal curve. And so you can see again that the mean of the sampling distributions, that the mean of all 500 samples is equal to the true population mean, or something really close to it within rounding. And the standard deviation of the sampling distribution is equal to the standard error. So basically what we've learned here is that it doesn't matter what the shape of the underlying distribution is. If the sampling distribution, as long as we have a sufficiently large sample size, 50 or more, and here we have 100, we're going to get a bell-shaped sampling distribution.